Thank you very much, Mikhail, for the kind introduction and for the invitation. Of course, it's a great pleasure to be here in Stockholm. I'd like to say, in spite of the, all these installations, I would like to encourage you to ask questions if things are unclear. So I don't know whether that works. I guess to start out here, I'd like to maybe mention that this is, of course, not only my own work. It's joint work with my former student, Bobak Nazer, who is now a faculty by himself, and a few more students, and also Shlomo Shammai from the Technion. So I guess any talk that has network information, or that has the word informations here in the title, should probably start with Shannon, and that's what I'm planning on doing here. Perhaps with a slight twist, I hope, as this first bullet item, which somehow compares Shannon and an Elias, an approach due to Elias. Then I'll start talking about network information theory from a very particular perspective, of course, biased towards what I want to discuss here, and then a few tools and that are connected to algebraic structure, I guess. So to get started, I guess that's the other obligatory thing to have as one's first figure, one that just has a simple point-to-point channel. What is this picture displaying is there is a message here, that's the data, being encoded into X, that's the code word, and then transmitted across this channel, which adds some noise here, of course, denoted by this conditional distribution, y given x. That's the channel output, the noisy channel output. The decoder has to figure out what this message was. The thing that we want to remember is there has to be a code book, so not all possible sequences at the channel input should be used, only a small subset of them, because you somehow need to be able to figure out which one was used from a noisy version. So that's what we'll call a code book. And so here there's a whole bunch of code words, right? In line with the standard information theoretic notation, it turns out to be useful to denote their number in this weird exponential form, and I'm sure that you all know why. So 2 to the nr, that's just the number of the total number of different messages. N is the length, the block length. So each of these code words is a sequence of n symbols. And what I want you to think about here is each of the symbols is a Q-ary symbol, for starters, right? And I guess that's the other thing, right? The talk about information theory should also have a picture of Shannon. Here's a particularly nice one with a famous curve in the background on the blackboard. I guess I could actually use the blackboard myself. So Shannon came up, amongst many other things, with a very beautiful argument that is often referred to as the random coding argument or the probabilistic method. And I have a very silly, admittedly, cartoon of that method here. I'll use this cartoon later on. So what does this depict? These are my channel input symbols. They are Q-ary, so there's 0 to Q minus 1 are the different possibilities. What is the second dimension? Well, the idea is this is the first symbol of your code word. This is the second symbol of your code word. Well, this is a pretty silly code, right? It has only 2 dimensions. In principle, there should be a third and a fourth and so on dimension, but I didn't find a good way of displaying this pictorially. So here are 2 dimensions. And then each dot here represents a code word. This code is terrible, right? There's far too many code words. Whenever you add noise, you will not be able to figure it out from this code. So what I ask you to do is imagine this in n dimensions. So imagine in n-dimensional space. Shannon's random coding argument was as follows. You pick these points uniformly at random, right? Or I shouldn't say uniform. Actually, you pick these points at random from some distribution. And even more so, you pick first the first component at random from some distribution over these letters 0 to Q minus 1. Then you pick the second component at random. Then you pick the third component, and you keep doing this. And you also keep doing this for each of the code words, right? Now, that seems a pretty silly approach, and of course, you all know how the story goes, right? Why is it still good? So what does the decoder do? And here is the genius, if you want. The decoder, from looking at this noisy output, just looks through the whole code book and finds something that looks jointly typical. That looks like it generated the output. Now, I like to refer to the key element here as the cuckoo's egg lemma. Namely, what is the key error event? The key error event is that some other code word, not the one that was transmitted, looks like it generated your channel output. It looks like it's the right thing, right? And the cuckoo, as you know, I hope, puts its eggs into the wrong nest, and the bird hopefully cannot tell it's a cuckoo's egg and will nevertheless breed the egg. So this is the probability that a cuckoo's egg will not be detected, right? So x tilde is the wrong code word. It's the cuckoo's egg. Probability that it will not be detected is And here is where the mutual information comes up, right? So the Shannon's beautiful invention actually comes up very naturally if you come from this cuckoo's perspective. It is upper bounded by this mutual information and exponential, I guess, in the block length n. So anyway, the only thing you need to remember is that this, the probability of the cuckoo's egg, it depends only on the fact that the wrong code word, the cuckoo's egg, is independent of what you receive. That's the key step, actually. So, but it looks like it's the right one, but actually it's independent, right? And then you use a union bound, and I should actually have deleted these equations here. I don't even want you to think about this. But what Shannon got out of this very simple argument is this beautiful capacity formula that I'm sure all of you have seen, which can be written just in terms of this beautiful information functional, and maximizing this over all possible distributions over these letters. I haven't told you really according to what distribution we pick each of the letter. Well, you get to pick it arbitrarily. You get to maximize this mutual information term. I'm not talking anything about whether you can do better or not. That's actually not a subject of this talk. And I'm sure that most of you know there's a completely different argument actually that shows that you cannot do better than this. So far, so good, right? That could be the end of the story. 1948, I guess here we have it. A few years later, and I also have a picture of Elias, Peter Elias here, another famous information theorist. Unfortunately, the resolution is terrible, but he's a great guy nevertheless. So this is an alternative version of the same thing, or almost. So what did Elias say? He said, well, let's not just pick these code words at random. Instead, let's do something else. Let's fix a matrix here, which are also letters in a Q-area alphabet, so between 0 and Q minus 1. And I'm always assuming, for those of you who are interested in that, that Q is a prime number here. So these are letters, again, from that same Q-area alphabet. And we think of now the message as written out also in that same Q-area alphabet. And then Elias's, or I should actually say, this idea goes back to Hamming, of course, and perhaps earlier, but I think usually Hamming. But Elias used it in a very particular way. So this is why I credit it here to Elias. So you create your code words in this very particular fashion by here picking the message according to the data you have, and then multiplying this into this matrix, and that gives you one of your code words, right? And so by varying over all possible message configurations, you'll space out the whole range of code words that appear. And of course, you can write this in very compact notation, and we'll use that later on, as just the code word x now is equal to sum this matrix G times a W. What Elias's approach was is as follows. He said, let's pick this matrix randomly, right? So that's kind of just going beyond Hamming's approach. You pick the generator matrix, this G matrix, the entries just randomly. And what happens to my little picture, that's the same picture now, 0 to Q minus 1, as in the Shannon case. And I'm first drawing all the possible code words of length 2. And what you can verify, I'm not going to prove this, but what you can verify is that if you do a code in this fashion, what you'll retain is a regular pattern. So I guess that's kind of the key difference. In Shannon's case, this was just a random pattern. In Elias's case, this is actually a regular pattern of dots. And now, of course, you can ask yourself again, how do you decode? Well, the key is, and I'm also not proving this, but the key is that the code words are still pairwise independent under this construction. That's not quite trivial, but it's also not very hard to prove. So you just trust me on this one. The code words are still pairwise independent, which still means that if you look through, you have received some noisy version, you look through all of the possible code words, the probability that the wrong guy will look like it generated your noisy observation is again given or upper bounded by the cuckoo's egg lemma, right? You can again say, it's a cuckoo's egg because it's independent. What's the probability it looks giant typical? You get your good old mutual information expression again. And the only kicker here is that, unfortunately, the distribution of the code words is now uniform. Another thing I'm not proving, but that's actually fairly straightforward to prove. Unfortunately, in Shannon's case, we got to pick the distribution of the x here arbitrarily. In Elias's version, it has to be uniform. So that's kind of Shannon versus Elias first take, and I guess I have it here on one slide. Shannon 48 showed you can get any rate, you can be as good as capacity. Elias showed essentially the same thing, except that x had to be uniform, and so that means that the linear structure of the code seems to impose, or does impose, a fundamental performance penalty in general. And I guess you can even show that this is really fundamental. That's shown by Algebraic also a very long time ago. That this is actually a fundamental limitation. If you want the code to have a group structure, then you will run into this problem. Let's not talk about these workarounds. So I want to now move on to network information theory and see somehow, this battle, Shannon versus Elias, a battle of the titans, to see how this evolves in that direction. So here is a very cheesy picture of a network. I have a bunch of wireless devices. Here they are. They're all kind of emitting some information at the same time. That's the kind of network I want you to think about. And like I told you, I will not do the standard introduction to network information theory, for those of you who are familiar with that. I will pick a very biased sample of network information theory. And here is a first one that you could imagine in this space arising. You have two guys who are interested, who each have half of the file, right? So this guy has the first half, W1. This guy has the other half, W2. And there's a relay helping them. Unfortunately, there's no direct connection, the way I want to think about it right now. But they have to go through the relay. And I think actually this, well, in this form, it was proposed in 2004. It dates back a bit further to Raymond Knopp at Eurocom, who looked at this even in the 90s, well, in the early 2000s. So this little problem here is a very interesting one for obvious reasons. I think it's file exchange or file sharing. And what could you be doing in this? What would you like to be doing in this little case here? Well, here is first one, which you could do. I call this time division. Well, you take turns, right? First turn is, so epoch or time step A is this guy transmits. Everybody else is silent. This guy transmits, and there's no direct connection, remember. So the only thing that happens is that this middle guy, the relay, will receive W1, right? Second epoch, second time step, this guy transmits. The relay will receive now also W2. In the third epoch, relay decides to send out W1, which this guy can receive. So you have W1 and W2 here now. And then in the final epoch, this guy transmits W2, and now both users are happy. I think an obvious and perhaps very well-known way of shortcutting this is the following one. You just say, oh, look, I only need 3 time steps. Why is that? Well, because one feature that you can see is that if this guy transmits, both users can hear, right, by wireless reciprocity or you name it, but both of the guys can actually receive. So what you need to send out, if you do it cleverly, you will take these 2 packets, these 2 halves of the file, and you'll add them, for example, in a mod2 fashion, right, just bitwise. And you send out this garbled version. Well, obviously, both of them can undo that garbling because each has one of the 2 parts, right? It's called network coding. What I want you to think about here, for the purpose of my talk, is, I guess I call it here, physical layer network coding. You look at this, you stare at this example again, and you think like, well, wait a minute. This middle guy never even needs to receive W1 and W2 separately. All he ever wants to learn is W1 plus W2, right? So it's kind of clear. It would be very tempting for this guy to directly decode W1 plus W2. So for these 2 guys to be simultaneously active, somehow communicating W1 plus W2 to the middle guy, and then this middle guy can send it out. So you could do it, if that were possible, you could do it in 2 epochs. Right? So that's a motivation number 1 for, and what I have in mind, I think many of you know, what I have in mind here, of course, is, so apparently for this to be possible, we need this guy to be able to decode directly the sum. Well, is that possible? Yes or no? Before I tell you this, I want to go through some more examples. Here's another old one that we have thought about for quite a while. Similar setup, except this time we have 2 guys that each have partial information which they want to transmit or communicate to a central hub, right, to a backbone or something. Except that, unfortunately, they cannot communicate directly to the backbone, right? Instead, they have to do that through the help of 2 relays or 2 other guys. Right, this guy and that guy. And the idea is that if you communicate up, I guess the uplink here, you could think, from these 2 guys to these 2 guys, there is some garbling going on. Unfortunately, it's wireless interference, signals go in all directions. Here is what I want to do for this particular example. I want to say that this relay station or this intermediate node receives the sum of these 2 transmitted signals, and this guy, for some weird reason, receives the difference. And now you can ask yourself, well, what should they be doing with this, right? So they have to somehow live with interference. How do you do that? Well, you could, for example, decide, well, this guy, even though there is interference, this guy just tries to decode x1. And that guy here tries to decode x2. right? That's one strategy you could do. And each relay chooses to decode one message. You could do something else. You could, for example, say, well, let's actually think twice. There's so much interference, maybe it's not a good idea to try and to decode anything. So instead, let's just quantize, right? Let's just somehow try to describe what I'm seeing and let this guy pick up all the slack. So this guy now would just quantize the received signal, the signal on the antenna, right, being quantized, and send somehow the best possible description of that signal to that guy. And this guy does the same, and then this person here sitting down here has to do all the work. That's this strategy here. How well do they do? You can see they don't do too poorly on this little example, but I have an upper bound that I'm not telling you how I got it. This is how much you could hope to get, and you see that there's a systematic penalty that you're paying. And again, I hope that you are thinking, well, the really tempting thing is this guy should probably just decode the sum of these two messages, and that guy here should decode the difference. Some of you might wonder at this point, well, sum and difference are the same thing. That's true in the binary world. I want you to think of these information packets here as encoded somehow in an alphabet, in a field of a characteristic larger than 2. So something where there is a sum and a difference. You can take, well, actually, you can take characteristic 2 and just take like, GF16 or something. If you could do that, right, that would be terrific. And indeed, I'll show you later on how to do it. But indeed, you get actually, at least in this larger SNR regime, you get exactly, or pretty much almost all the way to the upper bound if you do that, right? If you choose to decode this sum and difference. Good. So that's another challenging thing. And as a final one, a final kind of motivation of my egocentric version of network information theory, here is one of recent interest, at least in the community. Now we have many more terminals showing up, 2 times k. But what they want to do is very different from the examples that I just discussed. What is it now? Each of these guys has its own file. So user 1 has a file, W1, and only wants to send it to receiver 1. These guys don't care about the file W1. Right? It's called an interference channel in the information theoretical literature. Same thing for this guy, right? Second guy has a file W2, and it only needs to go to user 2. Anybody else is not interested in that. Now again, right, so I'm stretching your imagination here a little bit, but let's now think what happens to these signals, and let's again think that they are just kind of garbled together, right? Something happens to them, they're somehow washed together. You have to do something clever at this point. And here's one thing clever that you could do, in line with the stories that I've just told you before. You could let this first guy decode, again, some kind of a function, right? Here it is, some function that involves all of these information files, all of the information that this guy is not even interested in, but it's still captured in this function. Now, if by some magic reason, you could also decode, maybe at some later time, another function of those same packets, right? And that other function happened to be complementary in a certain sense. And somehow that magically happened for everybody, so everybody could decode 2 complementary functions. Then you can, of course, add your 2 functions, right? There's a lot of garbage, a lot of noise, interference in here that you don't know, but if you add them, it all drops out. It all cancels out, right? And so again, it hinges on you being able to somehow decode these crazy functions. By the way, this has actually very nice underlying linear algebra problems that I don't know how to solve, right? It's like a kind of at least not in general. It's like solving a linear system of equations, but you don't care about certain variables. How can you characterize this? Is there some equivalent rank criterion? I don't know. In any case, the main point being here is that in network information theoretic problems, it is tempting to do these, to decode functions of packets. Generally speaking, there's scenarios where it could be very beneficial if you only could do that. And so the first version of this that I want to discuss is this, what I call here compute and forward, which is somehow, Shannon versus Elias round 2. Maybe I should have called it like this. Here is a very simple snapshot of the problem that we are looking at. This is the simplest possible version. We have 2 encoders, right? Encoder 1 sending x1, encoder 2 sending another signal. They are garbled together. Maybe just add it up. There's some noise. And here is the kicker. You want to decode x1 plus x2, right? It's a weird problem at first. If I had just shown you this at the beginning, you should have told me, well, why? Why do we want to decode x1 plus x2? But I hope that these network information theory applications gave you somewhat of a sense of why this could be an interesting problem. And I guess what we want to look at is as a starter, again, just over a, what I call here, a finite field multiplex S channel. So what happens here, like in my startup example, I'm assuming that user 1 can send out these sequences of length n of symbols that are Q-airy, exactly like when we started out, right? And so, but now the kicker is that user 2 also sends that same, some other potential other sequence of length n of Q-airy symbols, and those are added up mod Q. Noise is added in mod Q, so it's a very artificial scenario, and the decoder gets this signal Y and needs to decode out, I guess like we said before, the sum of these two packets, right? So here is, Shannon's approach to this. We have the same exact pictures that I showed you at the beginning, right? So the dots are picked randomly according to the probabilistic method like Shannon uses it. And then these dots are added up. And now you see what happens. What happens is that you get essentially almost every dot. What have I drawn here? Every dot here is the sum of a dot from here plus a dot from here. Of course, modulo Q, right? So inside the finite field. And you can see that you essentially trace out almost the whole region, right? Not quite, but almost. And what does that mean? That means even if you could decode one of these points, you would actually know exactly what this guy was and what that guy was, because every sum point essentially uniquely determines which 2 points it came from, right? And that's the problem with I guess, Shannon's random coding argument in this context. And if you instead follow the Elias approach, right? So we use linear codes, and the trickiness for this case here is that we use, in fact, the same linear code on both encoders. So this was the Elias approach, right? You just take your message and you multiply it into this matrix. You blow it up into a code word x1. And user 2 does the same thing with the same code, the same matrix. Now, of course, the received signal in my very simple case, right, is just a mod sum of x1 plus x2 plus z. And that's where the algebraic structure enters, right? That's what you get for algebraic structure, is because then now you have g times w1 plus g times w2, but because everything happens in a finite field, you can pull out this g. And it is as if you had encoded the sum of the two code words, or the two packets, I should say, the sum of the two packets to begin with. And that gives you a certain rate. I don't want to talk about today exactly what that rate is, other than giving you at least a picture. Well, first of all, this little picture. So the same picture. Now for Elias version, what does it look like? Well, you remember it was a regular subsampling, right? If you use a linear code, you get a regular subsampling of that space. And if you add two of these regular subsamplings, you get another regular subsampling. So now you have exactly the property you wanted, namely each of these points will not uniquely identify a point from here and a point from here, but it will really only identify their sum, right? So in a sense, it's not giving you unnecessary information that you didn't even ask for. And I guess here is a little picture that shows how well this does, right? If you go with the Shannon random coding argument, you'll be down here. And if you go with the Elias approach here, then you'll be up here actually at this point, right? So it's a big difference for this little case. So I also need to say a few things, and I guess that's where it gets a lot more interesting and a lot more algebra entering into the field, is if we go to now a completely different channel model, namely the famous Gaussian channel. And I'm sure that everybody has seen this. Capacity turns out to be a half log of the effective signal-to-noise ratio. The channel looks like this. You get to input a real valued sequence now. You add Gaussian noise, right? Wide Gaussian process, and that's the output here for the receiver. And of course, the game is still the same. The receiver has to output an estimate of the channel of the message at the input, and then you can ask the same capacity question. It turns out it has the same formula, right? That's very beautiful from Shannon's argument. And you can draw similar pictures. This one here is taken from Cover and Thomas's book on information theory. It's as misleading if you want as the pictures that I showed you earlier. So maybe I don't have to apologize as much because these guys should apologize. But here are now, the idea is that every code word lives here at the center of one of these little balls. And the idea is the ball is the noise, right? So if you send this code word here, for example, that sits at the center of this ball, then you'll receive something that's inside this little noise ball, which is the high probability region of the Gaussian noise. And I'm sure that most of you have seen this earlier. And now, of course, we can make the same point about these random codes again. So Shannon's random codes for this Gaussian case also are not good for computation for the same exact reason. And perhaps here it's even more obvious. If you use just randomly selected points. In these figures, I have actually put the code words as well. You'll get this explosion of points, right? And the idea is now each point uniquely identifies, again, which 2 points it came from. And I think here it's particularly obvious. And you can ask the question now, how big can the noise be so that you can actually decode any of these points? And of course, if you pick this kind of a noise, then you have all hell breaks loose and you can never hope to decode. So this will not work, right? This system will not work for the same reason that the other one didn't work. And the question is, how does it work? What can you do? And I should say we have explored one approach. As you will see, we cannot prove that it's the optimal approach. So I hope that you will prove a better approach. I hope that you'll find a better approach and close these gaps that we have. What we looked at is a lattice code. So we look at, here is a lattice in 2 dimensions, again, with the same abuse of your geometric intuition. This is a lattice in 2 dimensions. It should be in n dimensions. And the idea is that we pick code words just from this lattice. And I guess I should mention one thing here that I haven't mentioned very well a few slides ago, which is on the Gaussian channel, we have a power constraint. Somewhere there is the origin. In my picture here, this is the all zeros sequence. And the power constraint means that you cannot send a point that's like way out here because that's just not allowed, right? That's a part of the Shannon, of the standard additive white Gaussian noise model. So, well, here I'm drawing for you also these noise spheres, which now turn out to be aligned with the lattice structure. But the thing that I have to do is I have to constrain to sequences that don't have too high of an L2 norm, right? So otherwise, they violate my power constraint. So my codebook will look like this. It will be one fundamental cell of this lattice. Why did I cut it out like this? I'm actually wasting something here. I'm wasting some power because I would be allowed to use some sequences that live here, here, and here as well, right? Because the L2 ball is a round surface. I've picked something that's aligned with the lattice. It turns out that that's actually a lot easier to handle and to deal with and to prove things about. And I don't think that that's where we lose. But I might be wrong about that. So maybe that's a footnote. So we use this code. We use code words that live in a fundamental cell of a coarse lattice that's somehow nested with a fine lattice. And the idea is, of course, again, the same thing as before. All the users use the same lattices. So for example, user 1 could transmit this point, user 2 that point. And then what happens? Well, the 2 lattice points get added up. Suppose that the channel does a straight up addition. You get this point here. And then you have to, of course, take the noise. The noise will push you out a little bit. But as long as you pick this cell big enough, you can live with the noise. You can decode. And you'll find back exactly the lattice point that corresponds to the sum of your 2 original points. So far, so good, right? Where does it get interesting? Where does somehow algebra enter the field again? Or I guess more than here, just is the minute you start deviating from the channel a little bit. And that's where it gets, I guess, more practical. So now let's assume that the channel does not just perform a straight up addition of these 2 lattice points, but that there's actually some fading going on. Or something, some attenuation of the signal by a coefficient here h1 and a coefficient h2. And those are outside of your control. So we assume that those are, depending on how the laptops are spaced are placed in space, so you don't really know what these will be. You have to somehow live with them, and we want to see how does this decoding sums and so on survive. So, I could have picked pi and the Euler constant, but for my example here, I picked, I guess, 1.4 and 2.1, but that's not really important, right? So these would be the signal. Well, it's amplifying the signal a little bit, but again, that's actually not the main point. So the signal is multiplied by something, and the important thing is that this guy does not know that there's going to be a multiplication by 1.4. Otherwise, it would be trivial, right? You could just undo the multiplication before you transmit it. Now what happens to our nice picture, right? First of all, you scale the orange vector by 1.4 and the blue vector by 2.1. You add them up. It's no longer a lattice point, right? So that's kind of pretty bad news. And the question is, what can you do? Well, on top of it, there's also noise being added. And now, you're in trouble. What can you do? Well, one idea that we came up with, and again, that might be lossy, is that we just decode to the closest lattice point nevertheless, right? So now we have to make, and I haven't done this in this slide here, but we have to make those noise balls a little bigger to allow for the fact that we actually also somehow get pushed away from where we would like to be by the fading, by the behavior of the channel, right? So here I picked, for example, I picked, for example, the point which corresponds to 1 times this orange point plus 2 times the blue point, right? If you think back to my examples on network information theory, that's actually still useful, right? If you have 1 times 1 packet plus 2 times the other packet, well, in the two-way relay scenario, that's still a perfectly useful thing to decode. So that's good. But of course, the problem is that that's not what the channel exactly did. So what you'll end up with is an effective noise that's amplified by, if you want, the self noise by this little penalty here. And that's, I think, where it gets interesting. That's where this integer approximation comes into play. The problem is all you can decode is integer combinations of these points. Because the lattice is an integer structure, right? Every point in here is, or every point in here is an integer combination of the two basic vectors of the lattice. So all you can decode is, all you can ever hope to decode is integer points, but the channel will not be integer. So you'll have this integer penalty, right? H is the channel, A is what you are decoding. You can make this, of course, by picking a good A. You can make this penalty as small as as small as possible, but it will be there. One follow-up idea that you might have is you take the received signal and you first multiply it by something, right? Why would you scale it? You change the length of the vector. Why would that be a good idea? Well, hopefully it brings you closer to an integer. That's a very old problem, of course. How do you, multiply? How do you scale something to get close to an integer? And in our case, for example, I guess you could pick a suitable multiplication and then decode to the point 2 and 3. Right, so you push yourself out further and get 2 and 3. But what happens, and here's what the price you pay, of course, whatever you multiply the output signal by, you also multiply the noise by. So you amplify the actual noise on the channel by betas. That's what you pay. But hopefully, if you pick a good beta, you can make this integer approximation penalty smaller. So what we have is, if you want, is a Diophantine approximation problem. I've shown this problem to many mathematicians, but somehow nobody has come up with a very good solution for, So what is the problem, right? Find the optimal beta. That's actually very easy. But then find the optimal A. I don't know how to do it. So I guess here are just the steps, right? So we decode to a sum of these packets and then come out with it. So this is the formula I had. I just showed you, right? So we have this beta penalty of the noise, and then hopefully we can make this integer approximation penalty really small. If you fix A and H to find the optimal beta, that's a homework exercise that is quite nice. It's essentially a mean squared error argument. The important problem, the one that I'd like to solve, is now maximize this character here over all H's. Or all A's, over all linear integer combinations that you want to decode. And I don't know how to do that, but I'd like to give you some intuition about this, that we found some ugly news and some better news. Well, I guess here is first, just for you pictorially, how efficient is it with this code construction that I have to decode the sum? Right now I'm looking just for kicks at a channel that is perfectly matched, so no fading, just for a sec. No fading on the channel. The channel is exactly the sum, and I'm asking you to decode the sum, but of course there's noise, right? So it's not an easy feat. And what you can see is if you use this lattice co-construction, that's how much rate you get per user. And if you decide to decode everything first, then you're down here. That's for 2 users, for 5 users, and for 10 users. And you see there's a huge gap, right? So that's again, Shannon versus Elias if you want, except that here, of course, we have to do it with lattice codes, not just with linear codes. Footnote, you can construct your linear codes from, you can construct your lattice codes from linear codes in a pretty straightforward fashion, and those will actually be reasonably good. And here is the quest, right? Here is the thing that we don't know. If the SNR is kind of smallish, then we go away from the upper bound, and at some point we even go under full decoding. Well, this you can avoid here by some trickery, but you will go away from the upper bound. And that's why I said I don't know whether this is the optimal strategy. I really don't know it. I just know that it's a lot better than if you go with Shannon's standard approach. And another thing you might be interested in, actually let me skip this here because I'd really like to get to this Diophantine problem. Perhaps somebody can help me with this. That's a one that I've been thinking about for a long time. So there is an inherent Diophantine approximation problem where you have your fading, it does something, it's not integer, and you have to somehow approximate it in the best way by integers. How good is that? The first study here that I'm doing is just numerical because I cannot solve the problem, right? So here I am just, hacking it into MATLAB. And what you get here is what I'm assuming is that these H1, H2, H3s, they are picked from IID Gaussian, so Rayleigh fading as it is usually called, picking these to be Gaussian. And I'm looking at, on average, how well do I do? So I just did a lot of simulations. Every time I find the best integer approximation, right? If you give me a, if you give me a real valued vector, I can find by testing, I can find the best integer approximation. It's not so hard. And you can see that on average, if we decode the equations or if we use the lattice code, we do actually better, right? Significantly better than decoding everything or treating the interfering guy as noise. So on average, it looks good. But now let's look at what happens instance per instance. And that's, I think, is a very instructive consideration. So now I'm making it even simpler so that we can see what's going on. I'm looking at the channel that has only two guys, right? X1 and X2. And for simplicity, I'm not fading X1. So there's no coefficient, there's just one. And then I have this coefficient H, right? And what we want to recover again is the best possible integer combination. I'm asking now, you have to decode a true integer combination, so you cannot pick either of them to be 0. And how does that pan out? So what am I showing you here? This axis is that coefficient H. I'm only going from 0 to 1. Of course, important to remember, transmitters do not know what H is. It's fixed this time. I'm not varying it, but the transmitters don't know what H is. The receivers do know it, but that actually doesn't make that much of a difference. So transmitters don't know H, and here is what you can see at the SNR of 10 dB. You see this behavior, so if you decode an equation, it's the same as decoding everything up until a certain point, up until 1/2. And then decoding an equation is significantly better. Here you have a little hiccup, but before I go to this, let me increase the SNR, 20 dB. Now what happens? Decoding an equation, right, so now this point moved down, so that's good. Decoding an equation starts being better already at around 0.3. And you see this weird up and down behavior, right? And that's exactly the Diophantine behavior. So let me jack up the SNR a little more, 30 dB, right? So you see the same behavior, 40 dB, wiggly behavior. And of course, what you start realizing, right, and I think a lot of you guessed it already, is that at 0.5, for example, you do very well, right? At 0.333, you do very well, right? 0.25, you do very well. In short, you do very well wherever this H is a rational number. And now I think all of you know that there's not too many, well, there's infinitely many rational numbers, but their density is 0 amongst the reals. So if you increase the SNR to infinity, you'll see that essentially you are stuck down at decoding both. So for a very high SNR, this is actually not a good idea. It's not hard to prove. It's essentially just because the rationals are not dense, right? Of course, you get significant gains whenever the SNR is finite, but when the SNR goes to infinity, it's not a good strategy. So that's another little challenge here. I would like to talk a little bit about, and I want to decide a bit what I want to do, a little bit about some of the applications and where some of this actually comes back in a very nice way. So let me skip this part here because it's fairly obvious and start, well, maybe I can say, so one thing that we of course were tempted by is then to show, can I find a network for which Elias's approach is unboundedly better than Shannon's approach, right? Can I doctor a network? And here is one. Just for completeness, this is what's called a multicasting. So this guy is streaming a movie to, in this case, this little example, 4 receivers. And the network is very carefully crafted in this particular fashion with noises added, of course, with these noises. That's where the Elias approach comes in handy, because at these points you will want to decode sums, right? It's exactly here where you want to decode these functions. And for this network, if you scale it up, so n is the total number of nodes in this network, if you scale up this network, you can see, and maybe I should have called it R Elias versus R Shannon, you can find that this scales like the number of nodes to the 1/4, but of course that's an unbounded gap. That's just to kind of cross-check that indeed this strategy, there are some networks for which this strategy is absolutely necessary. You cannot, you are far away. It's not just a little gap, it's not 10%, it's something that's growing unboundedly. The one thing that I'd like to mention here, perhaps also because it's a little closer to something practical, that's a collaboration with Shlomo Shammai and a few more, is this problem of rate-constrained cellular backhaul. So what is this problem? We look at here 3 neighboring cells. Each cell, we look at one time step, if you want. So we assume that each cell is somehow using TDM, time division. So in each time slot, there's only one user active. So we have one user per cell. And they're all of these base stations are connected through a rate-limited backhaul link to a central processor. It's something, by the way, that at least part of the industry is exploring. Last time I was at Qualcomm last year, they were still very excited about this. Of course, you all know how the industry is. I don't know whether they're still excited about it now because they are, moving around like crazy. But what this model looks like, in particular, what I would like to look at is what's called the Wiener model. So what I want to assume is that this mobile is heard by this cell and also by the neighboring cell, but not here. So I'm assuming, and the same thing for this. This mobile is heard by this cell tower, this one, but no further out. And so if you want, as another drawing, I could draw it in this particular fashion. Right, here is a, here are my cell towers. Each mobile is heard in 2 neighboring cells. Everything is perfectly symmetric. That's this assumption of the Wiener model. Might not be true in practice, and that's actually not what I want to emphasize. I just want to emphasize one little thing, which is again connected to my Diophantine approximation problem, because for some reason I'm a bit obsessing about that one. So the idea is, of course, that this guy will decode a function of the packets, right? Some coefficient c times xm plus b. And then all of these other guys will also decode functions. Now, what I want to assume is that, suppose for now, so change the situation a little bit, suppose that these guys, that these transmitters actually know what these alphas are, right? The problem is the alpha could be bad for you. Could be the Euler constant or pi or something, or 1 over pi. So then you are in one of these dips, right? And decoding equations is not a good idea. What could you do about it? How could you somehow, move yourself from a real number or an irrational number to a rational one? And here is one coding trick that you can use, which I find somewhat cute, is that you let one of the users use a part of its power for a private message and the rest for the code word. And how does this help, right? Right now it's not so clear, but here's how you do it. Here's one of these uplinks, right? This is the cell tower. This is the mobile in the middle in the cell, and these are the interfering mobiles. Now what you do is, at this cell tower, you first decode the private message, right? Could be a part of your packet. And then what you have now, of course, you have changed the effective, these now, you scale them all to be the same, but that way, by scaling the input to again have a 1 here, you have changed the effective parameter on these links, on these side links, right? So that's how you can, with this little trick of superimposing a different codebook, you can tune these interference parameters to be whatever you want them to be. And the same thing here, so the even guys, I guess, have 2 guys now that have a private message and 1 guy that doesn't. And the same thing here, you get a different parameter. And what does this trick buy you, right? So now you can play with your numbers a little bit, and you get something. I guess here, in this little example, this odd guy will be, of course, larger than h, and the even guy will be smaller than h, the original h. And you get a new network which has these asymmetric connectivities. And what this buys you, I just want to show you this picture here. What this buys you is the following thing. So decoding equations, if you don't do this trick of trying to steer towards the rational numbers, you are down here in this dashed line. And you can improve that quite a bit, I guess, by steering, by doing something dedicated about this issue of Diophantine approximation. And I guess you can see here what happens as I increase the SNR and also the backhaul. I guess you can see that it goes to where it should go, at least to some extent, right? You still see some effects of this Diophantine approximation always lurking around. So I want to not say too much about interference management and alignment. Maybe, so this was our example, right? And the question, of course, that you should have had about this is, why would it ever be the case that this guy could decode 2 complementary equations? And that guy also could decode two complementary equations. And one scenario where this does show up, which is a scenario that is very important to the emerging topic of interference alignment, is when this channel changes over time. How so? Right, so that's the idea. Now we assume that this channel changes over time. And importantly, for this part of the talk, I will assume that the transmitters know this matrix H. That's a very, very questionable assumption. So this is more of a gimmick than a real result. You have seen, I'm sure most of you have seen these interference alignment results out there. They also all assume that you have to know the channel at the transmitters and that there's a lot of time diversity in the channel. So those are all questionable. I think in terms of from the information series side, it's still very interesting. Whether or not it will make an impact on practice, we don't know. That judgment is still out. I'm very curious, of course, to hear your opinions on that later today. So here is the approach then, right? So if you have this matrix, which is a completely arbitrary matrix, you transmit your signal, you transmit your packet once. And then you wait until the matrix, the channel fading matrix, looks exactly like this. You see what have I done? I just switched the sign on these H12s through H1Ks, switch the sign here, but not on the diagonal terms. Right? You wait until this matrix happens, and then you retransmit the same packets. And that way you will be able to decode once this equation, right, efficiently, I should say, and once that equation efficiently. When does this happen? Well, you're going to tell me never, right? And that's exactly true. Of course, it will never happen because we are looking at a say Gaussian ensemble of matrices or something. So when will you have exactly this matrix and that one? You won't have it. But what you have to do technically is then, you say, well, within delta, right? The same matrix, but within a certain tolerance delta, and that now has a positive probability. And now you have to, of course, go through all of these arguments. Now, somebody once told me that every talk should have a proof, and every talk should have a joke. But the two should not be the same thing, right? I think you heard that one. In this case, maybe the two are the same thing because the proof of this, of course, well, it's not actually a joke. It still takes quite some effort to prove that this actually does pan out, right? So you have to look at the probability space. So we quantize. Actually, what we end up doing is we quantize the probability distribution, and then we use some typicality arguments. I don't want to do this here actually because I don't have too much time left. And you end up, I guess, with something that you can actually, you end up proving that you can, if you wait long enough, you will be able to pair up all of the matrices that you see to within delta, right? If you wait long enough. Now, of course, you have to wait quite for a long time until this actually works. And, I want to just mention this here. This is maybe one of the things, sometimes you get lucky in research. It's just a little gimmick at the end, which I'm sure some of you have seen, which is this idea. In the Gaussian case, actually, there is even a much simpler solution. So here we have the channel, all these received symbols at time t, when the matrix was H, right? And then here we have all the received signals at time tc, which is when this, when its complementary matrix showed up, this magic, matching up between two matrices. You might have to wait for a long time. But in this Gaussian case, what you can do is you can just add up these two received time slots, and you get a new channel, right? So now I'm doing it matrix by matrix. I get a new channel, which is just the sum of these two matrices. Let's write it out. The sum of these two channel outputs. Let's write it out, right? So this is at time t, you have just a matrix times x plus noise. At time t complement, you have this complementary matrix plus minus delta, times the same signal plus noise. So if you add up these two channel outputs, you get a total situation where everything goes away, right? And you have a diagonal matrix, no more interference. The interference is perfectly aligned up to delta, right? But you have twice the noise at this point. But the good thing is you also have twice the signal, right? And so in this case, actually, we do get quite a nice result, which this result is actually a lot stronger than the interference alignment result that was proved previously, which only holds for a large SNR. This holds for any SNR. And not only that, if you look at only phase fading, then this is actually capacity. So for special fading models, we can show this is the thing. This is the actual capacity. So yeah, so this was more in guise of a little cherry on the cake. I'd like to say that there's a lot more work in algebraic structural information, in network information theory. I've shown you my own biased view. We had a workshop this summer in Banff, organized together with Frank Krishang from Toronto, where I guess a lot of these people were present, talking about many of the applications of algebraic structure, the emerging ones in network network coding, I guess, and of course in interference alignment, but also in source coding. And so I guess, yeah, there's a lot more to be said about this topic. I should say, well, maybe I should have put this first. You might think that this is all just information theory, but some people are actually trying to implement this. Turns out to be a little tricky. These works here, Krishang, Frank's work, and also Krishna Narayanan's work, deal with the issue that what I have tacitly assumed throughout my talk is that this Q, all the lattices were somehow constructed over prime fields. Now that's a complexity issue. It's hard to design codes over prime fields. I'm sure some of you know that very well. It's not hard to construct them, I should say. It's hard to implement them. And so what you'd like to do it is over fields of characteristic 2, so GF2 to the something. Well, for this, you need an additional concept here, or one successful additional concept is this multi-level coding that Frank and Krishna were working on. We also have other people who have started designing these codes that actually allow you to decode functions. So it's not only information theoretic. I guess there is something to be said otherwise. So my concluding remarks would be, well, you know, for some of these examples, you really seem to need Elias, right? I should again have phrased it. Elias beats Shannon, you could say, right, in a silly way of speaking, for these for some of these network information theory problems, which is kind of cool because it was the other way around in point-to-point, right? The point-to-point Shannon was always better than Elias. Here, sometimes Elias is better. Applies to channel coding, that's what I've shown you, but also the source coding and even joint source channel coding, where I could have actually, I have a lot more work on that myself. And yeah, I guess another thing that I can say, a more complete set of these slides can be found on the website of the International Symposium on Information Theory this year in St. Petersburg, where Bobak and I gave a tutorial. Not all is included actually that I have here, but some is included in much more detail. And I guess there's a whole bunch of open problems. And I think the most important one that I'd like to see is some other code constructions for computation problems, beyond the ones that I talked about, so beyond the ones that come out of essentially Elias's and Hamming's approach into lattices, linear computation. Outer bounds is another one that I'd be very interested in. All the outer bounds I've shown you are just what's usually referred to in information theory as cut set bounds. They don't really take into account any of the structure of the problem, especially not the algebraic structure. Can we give any bounds that somehow show, for example, something like you have to have algebraic structure? I don't know. It could be hard. It's an ill-posed question, as I convinced myself after a few years, but I think there is still a version of the question that could be answered. I don't have the answer yet. Thank you very much for your time, and I'll stop here.